In the Chapter 15b PowerPoint, we will continue to examine at first the natural elements of global climate change, and this is the one I think is the most fascinating to me: variations in Earth's orbit. There was a Serbian astronomer in the late 1800s by the name of Milankovitch, who first proposed that variations in solar radiation occur due to three separate cyclic changes in Earth-Sun relationships, which we have no bearing on for obvious reasons, and they are known as eccentricity, precession, and obliquity. So now in the following slides, we're going to examine each of these cyclic changes in Earth-Sun relationships individually. And the first one we examine is called eccentricity. Eccentricity has to do with the shape of Earth's orbit around the Sun. The Earth's orbit around the Sun is not perfectly circular. It's a slight ellipse. At the moment, it's about as circular as it gets. And Milankovitch found out that it takes about 100,000 years for Earth's orbit around the Sun to go from almost circular to its most extreme ellipse to almost a circular orbit again. Now, right now, the difference in distance between perihelion, which is when we're closest to the Sun in January, and the aphelion, which is when we're farthest away from the Sun in July, is only about 3%, which results in about a 7% more energy received at the top of the atmosphere at perihelion, which occurs in January. So in January, the Earth as a whole receives about 7% more incoming solar radiation than it does in July. Now, this isn't a real game changer as far as Earth's current climate is concerned. But when the difference in that distance between aphelion and perihelion is as much as 9%, i.e. the Earth's orbit around the Sun is more elliptical, the top of the atmosphere would be receiving about 20% more energy at perihelion than at aphelion, and that, my friends, would be a game changer. With the change in orbit, the total incoming solar radiation doesn't change. This is assuming the Sun's output is the same. It's just the distribution of that incoming solar radiation. I will tell you that the illustration of eccentricity in figure 15.9 in your book is an exaggeration. All right, this isn't mathematically correct, but it's just to show you what a more elliptical orbit would look like. The second Milankovitch cycle is called precession. As the Earth spins on its axis, and because the Earth is so big, we don't feel this, but the Earth actually wobbles like a spinning top that's slowing down. And Milankovitch found that this was on a 23,000-year cycle. Now, at the present time, the Earth is, of course, as I mentioned, closer to the Sun in January than in July. Now, due to precession, the reverse will be true in about 11,000 years from now. In about 23,000 years, we'll be back to where we are today. So the bottom line is, if everything else remains the same, this means that in about 11,000 years, seasonal variations in the northern hemisphere should be greater than they are presently due to this wobble of Earth on its axis, which is called precession. Figure 15.10 in your book actually illustrates the spinning top effect. And then it actually shows that our conditions now in panel B is that we have perihelion in January and aphelion in July. Well, guess what? What will happen in about 11,000 years because of precession, we'll actually have perihelion in July and aphelion in January. Then it will go back to square one in about 21,000 years from now. The third Milankovitch cycle is called obliquity. This has to do with changes in the tilt of Earth's axis, which is, as Milankovitch found out, on roughly a 41,000-year cycle. Now, in the earlier chapter, we said that the tilt of the Earth from the plane of the ecliptic is 23.5 degrees from the vertical axis. And we said for that chapter, you can take that to the bank. Well, guess what? Over a 41,000-year cycle, this tilt angle actually varies from about 22.1 to about 24.5 degrees. Now, the smaller the tilt, the less seasonal variation there is between summer and winter in the middle and high latitudes, because if the tilt isn't as extreme, summers in theory would be milder and winters in theory wouldn't be quite as cold as they are now. Thus, as the next bullet point says, summers are cooler and winters are milder during a smaller tilt, but seasons are more extreme in a bigger tilt, i.e. the winters are colder and the summers then are hotter. This is an illustration from your book showing this obliquity and showing how the tilt just vary a little bit on this 41,000-year cycle. So it's interesting to note that this smaller tilt could promote cooler summers in the northern hemisphere. That would cause less ice to melt at the North Pole, meaning high latitudes, which actually over time may cause those ice sheets to expand if more ice, of course, is added to them over time. The current thinking about the total effect of the Milankovitch cycles is, when all the Milankovitch cycles are taken into account, the present trend should be toward cooler summers over high latitudes of the northern hemisphere. Now, this, of course, doesn't take into account the anthropogenic effect of climate change, which we haven't even gotten to yet. We are still only talking about the natural effects of climate change. And when you take all the Milankovitch cycles together, they point to cooler summers over high latitudes in the northern hemisphere. Remember that climate project I told you about that scientists worked on? I told you about that in 15A. Well, in the 1970s, the scientists of the Climate Project found strong evidence in deep ocean sediments that they examined that variations in climate during the past several 100,000 years were closely associated with the Milankovitch cycle. So they're saying, hey, we've got computers now, and if we work in reverse, looking at these sediment cores from the ocean, Milankovitch was onto something here. More recent studies suggest that over the past 800,000 years, ice sheets have peaked about every 100,000 years, and guess what? That coincides with eccentricity in the Milankovitch cycle, and scientists surmise that eccentricity then could be a forcing factor in these glaciations. Smaller ice intervals show up at intervals of about 41,000 years, and of course that would go with obliquity, and 23,000 years, which would go with the precession. However, orbital changes alone are probably not totally responsible for ice buildup and retreat, because further analysis shows that both carbon dioxide and methane tend to decrease during colder times, i.e. they tend to increase during warmer times. Additionally, temperature changes thousands of years ago preceded the CO2 changes, which means the temperature changes may be acting as a positive feedback mechanism along with the CO2 changes. Why atmospheric CO2 levels have varied as glaciers expanded and contracted really isn't clear yet to scientists. There are many, many possible factors. Now, this graphic looks rather complex, but I'll try to sort it out for you. It's 15.12 from your book. This actually comes from the research of the Intergovernmental Panel on Climate Change, or IPCC. And what it shows is these are ice cores from Antarctica, all right, that they studied, scientists studied. It shows how the atmospheric carbon dioxide concentrations and atmospheric methane concentrations tend to pretty much dovetail along with the temperature trends over Antarctica, which is very, very interesting. It's an analysis of the oxygen isotopes trapped in the ice. And remember, in 15A, we discussed what oxygen isotope analysis is all about. Very important element in proxy data in the study of Earth's changing climate. One thing we're not really well versed on yet in science is variations in the actual energy output of the sun, variations in solar output. This graphic, 15.14, actually shows some research that was done in the 1990s about the period during the 1980s, which seems to suggest that decreasing sunspot activity also means a slight decrease in solar output. It may have been responsible for what we call the Little Ice Age in Europe during the 1500s to the 1700s. There's a lot we don't know about the sun yet. We just now have got instruments in space to study the sun with greater depth. What about atmospheric particles? There are lots of particles in the sky. Microscopic they are. Need a microscope to see them. They're so small. They're liquid particles and solid particles. They enter the atmosphere from both natural and anthropogenic sources and do have an impact on climate. For now, we're talking about the natural atmospheric particles. It's a very complex relationship between these particles in the atmosphere. Volcanic eruptions have the greatest potential here as far as the natural causes of atmospheric particles, especially those volcanic eruptions that are rich in sulfur gases, because they combine with water vapor in the presence of sunlight to produce haze, and haze tends to reduce incoming solar radiation for as long as a few years to several years, depending on how much volcanic activity you actually have. In recent years, we have seen the eruptions of El Chicon in Mexico in 1982 and Mount Pinatubo in the Philippines in 1991. Those were significant volcanic eruptions in modern times. Pinatubo put out about twice the sulfur dioxide as the one in Mexico. Mount St. Helens, by the way, in 1980 in Washington State was not significant compared to these two. Estimates suggest a half a degree Celsius cooling occurred worldwide due to the Pinatubo eruption in 91, and that cooling may have been greater if not for an El Nino pattern in the equatorial Pacific Ocean waters at the time. Very, very interesting indeed. Here is a picture of that Mount Pinatubo eruption in June of 1991, showing the tremendous amount of particulate matter that went into the sky, and lots of it went up into the stratosphere then, which had the impact of decreasing in reflecting back to space a certain amount of incoming solar radiation. This graphic shows the results of research which indicates the slight decrease in Earth global temperatures in 1992 after the 1991 eruption by Mount Pinatubo in the Philippines. More on atmospheric particles. In 1815, there was a major volcanic explosion in Indonesia of Mount Tambora, and there is anecdotal historical evidence in the northeastern U.S., as people wrote things down, and also in Western Europe, that in 1816 they had a year without a summer, and then in the northeastern United States and in southeastern Canada in 1816 they actually had killing freezes which killed crops in the summertime. So there could be a relationship there. It's hard to tell, but there may very well could be a relationship there. Evidence suggests that when annual ice layers in Greenland and Antarctica are more acidic, that corresponds with a cooler climate. And scientists suggest that maybe that might be the cause of Europe's little ice age from about the mid-1300s to about the year 1700. There are also aerosols in the atmosphere. And this now leads us to a discussion of the often controversial, doesn't have to be because we've got science to prove it, anthropogenic contribution to climate change, i.e. human beings changing the content of the atmosphere because of factories, automobiles, aircraft, power plants, burning of fossil fuels, all these things. Sulfates and nitrates reflect incoming sunlight. Soot readily absorbs sunlight. Now, sulfate aerosols have been extensively researched by scientists. They tend to stay in the lower atmosphere for only a few days. They often get rained out or snowed out. And they primarily affect the northern hemisphere. Why? Well, that's because where most of human industry is that burns fossil fuels is in the northern hemisphere. Here's more on the effects of anthropogenic aerosols. Sulfate aerosols reflect incoming solar radiation back out to space and serve as cloud condensation nuclei that helps in the formation of clouds. And scientists have found that they tend to have a net cooling effect. So this might explain why the industrial regions of the northern hemisphere, that's what that means, NH, it doesn't mean New Hampshire, northern hemisphere, have warmed less than the southern hemisphere during the past several decades. It might also help to explain why the United States has experienced less warming than the rest of the world, and why up until the last few decades most of the global warming has occurred at night and not during the day, especially over polluted areas. So the sulfate aerosols that we human beings put into the atmosphere have some interesting effects. Let's talk about greenhouse gases. We know those are gases in the atmosphere that tend to retain heat down in the lower layer after it's sent back out to space by the surface of the Earth. These increasing levels of greenhouse gases are due to the burning of fossil fuels and deforestation. The relationship between increasing carbon dioxide and increasing temperatures is well established in science. Prior to the Industrial Revolution, the carbon dioxide content of the atmosphere was about 280 parts per million. Now it's about 390 parts per million. Chlorofluorocarbons, methane, and nitrous oxide are also increasing in the atmosphere. All are considered to be greenhouse gases. Land use change is very important when it comes to anthropogenic effects on the climate system. If you change a rainforest to grazing land, that's going to cause a decrease in evaporative cooling. That could lead to warming in those areas by several degrees Celsius. Land that is deforested tends to turn into desert as well, especially when you overgraze and overfarm on marginal land in the first place. A scientist by the name of Ruderman from the University of Virginia suggests that without pre-industrial farming 8,000 years ago, Earth would have actually cooled cooled off. So the anthropogenic greenhouse gases that we released 8,000 years ago actually maybe thwarted an ice age. We have just finished PowerPoint 15b.